Our next example is going to be another pin and roller supported beam, but this time we're going to move the pin over a little bit so it is no longer simply supported. We've got a cantilever now. I'm going to add on here a 30 kilonewton point load, and the distance between my point load and the pin is 2 meters. And the distance between my pin and my roller is 4 meters. I shall name you A, and you will be B. I wish to find the maximum deflection between A and B. All right. Elastic curve, remember it's how it's deformed. So remember that there's no vertical deviation at A, no vertical deviation at B, and it's going to be pushing down here at 30. And I've got nothing to change the shape between A and B, which means it's going to bow up and come back down here. Now this is not symmetrically loaded, not symmetrically supported, so the maximum deflection is not going to be in the middle, but I bet you it's going to be real close. All right. I also am going to set up some ordinates here. So there's my vertical deviation V ordinate, and then X will be from the left at A all the way over. Okay. This system has two curves. There's going to be one curve between the load and A, and then there is a second curve between A and B. So I'm going to have to do two sets of free body diagrams for this one. All right, so free body diagram 1, and again I'm going to take that to the left. Looks like this, a little bitty chunk here with the point load of 30 kilonewtons, and this is going to represent 0 less than or equal to X less than 2 meters. Should I put units on there? I should. A is at 2 meters, so it's not going to be included on my free body diagram here. But my distance X is, and since I have two sections, I'm going to give these a subscript: shear 1, normal 1, moment 1. All right. Again, I don't care about the shear equation. I'm just going to go straight to moment, because moment is what I integrate to get to slope and deflection. So some moments about the cut or the section is 0. 0 is equal to 30 times X plus M1. So M1 is equal to negative 30X. And then my slope, EI, is equal to the integral of the moment x dx, which is going to be negative 30x squared divided by 2 plus a constant of integration. And I'm not putting units on here, but that's going to be in kilonewton meters, which means this one is going to be in kilonewton meters squared. And then I have my vertical deviation, EI, which is the integral of the slope, x dx, which is going to be negative 30x cubed divided by 6 plus C1x plus C2 in kilonewton meters cubed. Now I need my second free body diagram. So this one's going to be a little bit longer. Okay, I'm starting over again at the origin. I do not ever want to take a cut-to-cut free body diagram, because that's just messy and gross, and we don't do it. I didn't write it up here, but I solved earlier that AY is equal to, what is AY equal to? 45 kilonewtons up, and it didn't matter until I got to this free body diagram, where you are 45 kilonewtons up. AX doesn't matter, but it's 0 if you care. We have V2, normal 2, and moment 2. Why am I writing all these down even though I'm only solving for moment? Because I'm a nerd and I want to take into account all of my distances. Okay, so, or all of my forces. Those are forces. I'm drawing a distance. Can't talk and write at the same time. But I want to take into account all my forces. Shear and normal still exist. I'm just not solving for them at this time. It is still 2 meters between 30 kilonewtons and A, and then my entire length is X. But these equations are only going to be relevant for X is greater than 2 meters and less than or equal to 6 meters. Okay, and this is all because of where I put my origin. I put my origin at the far left, so that means all my points have to be measured from the far left. Okay, don't worry, we'll do another example where that's not the case. Okay, so again, summing moments about the cut is equal to 0. Counterclockwise is added to my equation. I have 30 times X and minus 45 times X minus 2 plus M2. And I'm going to find that M2 is equal to 15X minus 90 kilonewton meters. Okay, so my slope 2, oh, I'm not doing very good on subscripts, add 1s up there. Slope 2 EI is equal to the integral of M2x dx, which is equal to negative 15x squared divided by 2 minus 90x plus constant 3. This is a new constant, so it gets a new subscript, kilonewton meters squared. And then my vertical deviation, I'm going to scooch this over a little bit more. EI is equal to the integral of my slope. And U are equal to negative 15x cubed divided by 6 minus 90x squared divided by 2 plus C3x plus C4. C4, boom. Just kidding. Kilonewton meters cubed. Okay, now that I have these, I'm going to do exactly like I did with the first problem and solve for the boundary conditions. Where do I know the answers? Okay, so we know the pen and the roller have V equal to 0. Okay, the pen is located at X is equal to 2 meters, and the roller is located at X is equal to 6 meters. All right, so now we have to think about this. So our X equation, and this is where this whole equal sign, not equal sign comes into play. As far as slope and deflection goes, at 2 meters, the slope and deflection is the same no matter which set of equations we use, which means that I can use V1 and V2 set equal to 0 to solve for my pen. My pen is at 2 meters and X is covers 2 meters in both sections, V1 and V2. So I'm going to start with V1. So V1 is equal to 0 at X is equal to 2. So 0 is equal to, I don't have to do that, I've got my notes over here. Negative 30 times 2 cubed divided by 6 plus C1 times 2 plus C2. Oh, yeah. Yay! That kind of got me nowhere. V2 is equal to 0 at x is equal to 2. These are in meters. So 0 is equal to negative 15 times 2 cubed divided by 6 minus 90 times 2 squared divided by 2 plus C3 times 2 plus C4. Okay, I have two equations, four unknowns. Fantastic. Okay, my roller is at 6 meters. The only set of equations that covers 6 meters is the second set. Okay, this first set stops at 2 meters. So if I want the rest of the curve, I have to use the second set. V2 is equal to 0. And again, this is lowercase v for the elastic curve, not shear. Okay, that's the exact same equation. I'm going to scooch this down. Negative 15 times 6 cubed divided by 6 minus 90 times 6 squared divided by 2 plus C3 times 2 plus C4. Hey, I've got two equations and two unknowns, and using whatever system of simultaneous equations makes you happy, we find that C3 is equal to 230 and C4 is equal to negative 300. Okay? Now I'm still stuck with C1 and C2 that I don't know. All right? So here are where continuity conditions come in. Continuity conditions are where there's overlap, okay? And we already know that there's overlap at 2 meters because the pin's there and deflection is equal to 0. So if the overlap applies to deflection, guess what? It also applies to slope. So at x equals 2 meters, slope 1 is equal to slope 2. All right? So we will have negative 30 times 2 squared divided by 2 plus C1 is equal to 15 times 2 squared divided by 2 minus 90 times 2 plus C3, which we found to be 230. We have one unknown, one equation. C1 is equal to 140. So that can now plug in up here. You are now 140, and we will have C2 is equal to, wherever that answer is on my notes, negative 240. Okay, got a lot of notes here, obviously, because look at all this work we're done, and we haven't even answered the question yet. So the question is, so now we have all of our constants and our equations, and the question is, where's the maximum deflection? Now there's two ways to do this. First, we can plot out every millimeter and then pick the largest value, or we can look where there's maximum deflection. Now remember, I told you earlier that slope at any point is that tangent. So if I look up here at this elastic curve and I draw a tangent line here, theta is equal to 0 degrees. And that's where my curve changes from increasing to decreasing, and guess what? That's going to be where my maximum deflection lies. Okay? So we need to find that distance. So I'm going to come down here. Maximum deflection is where theta 2 is equal to 0. Now I'm being very specific that theta 2 is equal to 0, because again, coming back to our elastic curve, our maximum deflection for the first 2 meters is just at 0. Okay, so this is also a deflection maximum, but I asked you specifically for the deflection between A and B, and in that case we have a curve shape and we need to find that vertex where theta is equal to 0. So down here we go. All right. We will have 0 is equal to 15x squared divided by 2 minus 90x plus 230. So this is my theta 2 equation, by the way. All right, and I'm going to solve for x because x is going to be where theta is equal to 0, and we get 3.7 and 8.3 meters for our two answers. Okay? Now our x2, our x for theta 2, has to be greater than 2 and less than or equal to 6 meters, which means this value is no good because it is greater than 6 meters. So this is our only x value. Yay! Which means this is where our maximum deflection occurs. So Vmax is at x is equal to 3.7 meters. So now I can plug that in. VEI is equal to 15 times 3.7 cubed divided by 6 minus 90 times 3.7 squared divided by 2 plus 230 times 3.7 minus 300. And this will be in kilonewton meters cubed. And we get that value, Vmax equals to 61.6 kilonewton meters cubed, and I'm moving over the E and the I. I wasn't given any values for that, so I'll leave them in variable format, no big deal. And this is our answer for the maximum deflection between A and B.